What's up, Albert?
Hello, Neil.
So tell me about the AFM experiment you are doing for SP2251.
You mean atomic force microscopy?
Yeah.
Alright. AFM was first developed by Binig, Quit and Gerber in 1986 as a collaboration between IBM and Stanford University. There are three primary modes of AFM: contact mode, non-contact mode and tapping mode. I will only talk about contact mode and tapping mode because non-contact mode is rarely used due to its limited application.
So what is the difference between contact and tapping mode?
Okay, let me start with contact mode first. Here is a schematic diagram for contact mode. Look at the tip. The tip is scanned across the sample surface by moving the scanner in XY position. The tip contacts the surface through the adsorbed fluid layer on the sample surface. There will be an attractive force between the tip and the sample. The change in cantilever deflection, due to the force, is monitored with a slit photodiode detector. A feedback loop maintains a constant deflection by vertically moving the scanner in the Z direction at each surface point. Eventually, a topographic image of the sample surface can be formed according to the vertical position of the scanner.
Okay. So how about the tapping mode AFM?
For tapping mode, the cantilever is oscillated at resonance frequency by piezo material while the tip is scanned at each surface point. The resonance frequency or the resonance amplitude changes according to van der Waals attraction between the tip and the sample. The feedback loop maintains constant oscillation amplitude by vertically moving the scanner in the Z direction at each surface point. From the change in the vertical position of the scanner, we can extract topographic information about the sample surface.
Wow, you know a lot.
Of course, I am Einstein.
So Bert, can you tell me more about what you do in the laboratory?
Sure, this is the sample I used. It is a standard grid used for calibration of AFM instruments supplied by the manufacturer.
Okay. What is the result?
Okay. Take a look at this image. This is an image of a region of the sample. The sample has 4 regions with different patterns. This image shows a region with circular wells. The different colors correspond to different heights. And then this is an image of another region of the sample. As you can see, this region has strips with alternating heights. By the way, these images are obtained using tapping mode.
Wow, you have cool images there.
Let me show you something cooler. This is a 2D image, right? This is an image of CD stamper. You see here there is a crack at the bottom left. There is also some dirt at bottom right. So this sample is quite dirty. Ha 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 ha. Now I am going to generate a 3D image of it.
Awesome.
To add to the awesomeness, I show you here how to measure the diameter of the well. First I draw a line along the diameter of one of the wells. Then watch how I place the 2 orange arrows on 2 sides of the well, along the line. And look and behold, that's it, we can now read the width of the well.
Fascinating. The level of awesomeness is over 9,000. Can you shower me with more awesomeness?
My pleasure. Here you go. These are photos taken during my experiment. Enjoy.
Wow! Nano things are way too small for you or I to see. But soon the world will change because of nanotechnology. 1,000,000 nanometers that are lined up in a row are just about as long as a single flake of snow. Even germs are several thousand nanometers tall, so when you hear that something's nano, it's very, very small.
I think that is very interesting.
Well, I think that's very lame.
Poker monster. Miss Glory, why is smaller better?
Well, you see, big plastic tubes do not exactly have a great appeal, but nanotubes are stronger than the strongest piece of steel, and they're lighter than most metals, which makes them so ideal. And maybe later a space elevator may truly become real.
Ooh, a space elevator.
That's not possible.
Nano, 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 what a wonderful surprise. That ordinary is extraordinary when you make it nano size. Grains of sand do nothing when they're sitting on the shore, but nano sand glows brightly like no light has done before. They shine all sorts of colors, from red to green to blue, and they use much less energy than current light bulbs do.